All right, welcome back. I hope you're having an awesome time so far. Our next speaker is Alishba Imran. She is a machine learning developer at Hanson Robotics and Kindred.AI. Please join me in welcoming Alishba to our virtual stage.
Awesome. So in 1858, artificial limbs were improved to look and feel more natural to human biology. Douglas Black from New York was one of the key inventors who developed an artificial leg that incorporated new technology, materials, and design to better mimic the natural movements of the human leg. Shortly after his invention, the Civil War broke out, and with the increasing number of disabled soldiers, we needed new and advanced prosthetics. However, to this day, the core tech and design behind prosthetics has not actually been significantly innovated upon. For this reason, expensive and difficult to use prosthetics is a global problem in our world today. The WHO has estimated that 150 million people globally still don't have access to prosthetic devices for these reasons. And prosthetics today can cost anywhere from $10,000 to $100,000. And it can take anywhere from 3 months to even a year at times to get used to actually training these and using the arm within a physician's lab or clinic. And even after you do get access to the arms, you usually have to manually manipulate them on a day-to-day basis to pick up or interact with different objects within your environment. Now, technologies like AI are allowing us to discover and build cheaper and more automated and efficient alternatives to machine and devices like prosthetics that interface with humans. This work is being developed at the intersection of AI, rehabilitation tech, humanoids, and medical devices. For example, by applying AI and additive manufacturing techniques like 3D printing to prosthetics, I've actually been able to develop my own version of a prosthetic that is able to reduce the cost from $10,000 on average to just $700. And I've also made prosthetics a lot easier to use and more personalized per amputees. Now, to get a better understanding of this work, we first need to understand the key areas within a subset of AI, which is machine learning. The main areas are supervised learning, unsupervised learning, and reinforcement learning. Within supervised learning, you're looking at classification of information such as image classification and diagnostics. With regression, you're making some sort of prediction or forecast in the future. And on the other hand, unsupervised learning looks at dimensional reduction, which includes big data visualization and image recognition techniques as well. This also includes clustering, which is commonly used within marketing and recommendation systems. And then finally, we have reinforcement learning, which is used for making real-time decisions and commonly within robotics for tasks such as navigation, manipulation, and gaming. Now, supervised learning is a concept that focuses on labeling of training data. And so the model first learns from the given training data that you provide it. And the training data contains different patterns, which the model will learn. But this data will contain inputs with the corresponding outputs, which it should have, as well as the hidden patterns within it. And the algorithm will learn these patterns and try to essentially apply these the same knowledge to unseen data with the aim of being able to predict some sort of future values. Mathematically, supervised learning can often be shown in the most simple form as just a simple linear function. Now, unlike supervised learning, we do not need to label the data for which we want to train the model in when it comes to unsupervised learning. The model actually just learns through training itself from the data and then discovering hidden patterns within it. Reinforcement learning is similar to the way that humans learn, which is through a process of trial and error. If you imagine you have a robot that you call your agent, in this case, you're trying to train the robot to try to walk just like humans would. So your goal here is to get that robot to walk successfully. The robot will go through a process of trying to walk, maybe failing a few times, trying again, until eventually it learns how to walk. And it learns the correct way to walk through reinforcements. So it gets a positive reinforcement or reward every time it walks correctly and a negative reinforcement every time it walks incorrectly. And there's many ways in which machine learning can be applied to enhance human-machine interfaces. One of these ways is through applying it for sensing and perception. So sensors are used in this scenario to sense the environment, and ML can be applied to process this data, compute the difference in the present state that the robot or machine is in, and the goal state that we would like it to be in. Using this, actuator commands are created to move the machine or robot and then sent to the actuators, which eventually do the action and act on the environment. Another common example is for manipulation of a robot or machine. Here, sensory input is taken, which can often be in the form of images. This is sent through a neural network for which a manipulation prediction is made, such as a specific grasping pose that the robot should do, and the control is then executed through a velocity command. As an example, let's say you have an RGBD sensor, and that is used to capture images of the objects in the workspace. The algorithm for manipulation is trained on a broad range of different objects and then tested on a new set of objects never seen before by the robot. Using ML, we can also bring human in the loop within the feedback. And so a common example of this is using reinforcement learning, where an agent is exploring and interacts with its environment. And so periodically you can train this agent with clips of the agent's behavior, and these are sent to a human operator. And this human operator can then actually select which one of these demonstrations best showcases steps towards fulfilling the desired goal. The human's choice is used to further train a reward predictor, which in turn trains the agent. So over time, the agent learns to maximize the reward from the predictor and improve its behavior in line with whatever the preference of the human is. Now, as mentioned, to improve prosthetics, I actually worked with a professor and master's student at San Jose State University to develop a new generative grasping neural net that uses techniques like convolutional neural networks and reinforcement learning to fully automate the process of identifying, grasping, and interacting with different objects with the prosthetic arm. By 3D printing the arm with a new material and design, we were also able to reduce the cost of the prosthetics from $10,000 on average to just $700, making the arms much more accessible and cheap and affordable to people globally. I also received mentorship from developers at Maya and researchers at the Blink Lab who supported me a lot on developing this work. And we're currently working on publishing this research in IMECE as well as IROS this year. So current prosthetics are controlled directly via the user's myoelectric signals. Now, these are essentially just signals that contain electrical activity of the muscles recorded from the skin surface of the stump. And so a myoelectric band is used to capture these signals and understand the user's intention. This, coupled with the camera on the prosthetics, is used to capture an image of the objects in the environment and process these by extracting key features such as what objects are in view. These images are then sent through a generative grasping CNN to make a prediction for the best grasp to grab that object. And then the identified grasp and myoelectric signals are sent to the prosthetic controller for proportional control and execution. The GGCNN I'm using provides a real-time generative grasping pipeline. The way it works is there's a camera mounted onto the wrist of the robot that captures depth images containing an object to be grasped. This GGCNN generates antipodal grasps, which are parameterized as a grasp quality, angle, and gripper width for every pixel in the input image within a fraction of a second. The best grasp is then calculated and a velocity command is sent back to the robot. This closed loop system is capable of grasping dynamic objects and reacting to control errors. This works by grouping objects by size, shape, and orientation according to the type of grasp that would be needed to pick them up. And so we essentially looked at 4 different key grasps in order to do this. This work does not just apply to prosthetics, but can actually be further extended to other rehabilitation devices such as hand exoskeletons that are used for recovering motor function of the hand for stroke patients. We can use soft robotics and machine learning for the development of low cost and easier to use portable rehabilitation gloves for stroke patients. These often contain a glove where the fingers are covered by soft actuators and the sensing and control is run by ML for individual control and sensings of the fingers. And then the entire glove is pneumatically controlled. When you get a stroke, there's often a golden period with optimal recovery of hand function, which occurs typically within the first 3 months after a stroke. We want to be able to improve hand motoric functions within this period through identical and repetitive movements by the impaired hands. And the main reason is because our brain recognizes this due to neuroplasticity after the stroke to help us eventually recover our motoric function. Now, globally, 15 million people suffer from a stroke worldwide. And of these, 5 million people die and another 5 million are permanently disabled. Traditional hand exoskeleton devices are really limited because of their high cost. They're very rigid. They weigh a lot. There's also constraints on the joints and the non-actuated degrees of freedom that pose a lot of complications. And these problems really stem from their components and the design of the exoskeleton, which contains linear actuators and rigid linkages. Now, soft robotics have a huge advantage to solve this problem due to their higher flexibility. They're also safer, lightweight, and a lot more simplified to actually produce, which results in a lower manufacturing cost. We can also use 3D printed materials to actually create actuators, which further reduces the cost. And soft robots are capable of generating forces and torques to support bidirectional finger movements, which are really important for recovering motoric functions. So this includes finger flexion and extension. The soft robotic glove passively controls the finger extension by the very finite elasticity of the actuators based on the pneumatic system it has on fluid decompression. So because soft robotics are so flexible, though, they do have limited output force, whereas where the soft robot hands need to be able to supply a strong force when actually grasping various objects in their environment. And so the development of control algorithms is a huge challenge for soft robots because of the nonlinearity of the soft actuators and how they interact with the environment today. Existing controllers proposed can be categorized into three main controller types. So there's model fit controllers, which are usually based on machine learning techniques or empirical methods. These controllers have really high advantages because they're highly nonlinear, non-uniform, and can work in unstructured environmental situations where modeling is impossible. Then you have model-based controllers, which usually need some sort of analytical models to drive the controller. But these controllers can be more accurate and reliable than model-free controllers. But they do require well-defined dynamical models for the soft robots, which is really difficult to construct based on rigid body assumptions. Then you have hybrid controllers, which is a combination of basically model-free and model-based controllers. And these are usually based on analytical models to capture the main part of the system's intrinsic properties, and then data learning model or machine learning model to compensate for dynamical uncertainties that might exist. These soft robot-bodied agents can also be controlled with the aid of RL by making machines that are able to execute and identify optimal behavior in terms of a certain reward or loss function. So within a typical RL problem, there's a learner and a decision maker called an agent, and the surrounding which it interacts with is called its environment. So the environment in turn provides rewards in a new state based on the actions of the agent. So in reinforcement learning, you don't have to explicitly teach an agent how it should do something, but present it with rewards that help it understand based on something being positive or negative for it to actually learn. So this can be done through the Markov decision process, which basically is used to train an agent to find a policy that will return the maximum amount of rewards from taking a series of actions within a few states. And so in this scenario, I used a function approximation Q-learning to train the control policy. So each episode, the soft robot executes a sequence of actions from the initial state. On the basis of the above state action reward representation, a final action is then introduced. So this action does not affect the shape of the robot, but indicating this episode will be stopped. So the entire learning process consists of repeating episodes from the initial state to the final action. Because of the continuous space and nonlinear setting of the problem, I mapped the state space into a higher dimensional linear space. This data structure can be seen as a neural network with only one hidden layer. And so this data structure is then fit into the Q function, which is basically the mean value function associated with the step numbers. I simulated the control of a soft robot gripper using approximation Q-learning to train the control policy for a simple manipulation task. So this was done with the Sophia toolkit using soft robotics, which is created by the Harvard Biodesign Lab. So here's a quick demo of what that actually looks like. So this simulator can also be used to sample in the state space before any reinforcement learning. So you can actually randomly execute actions and compute the Q value within each sample. So by sampling the state space, you can use the gradient descent algorithm to actually compute the weights of this network, and then use the Q function trained in this way as the initial Q in the simulation step to help the model reach better performance. In terms of execution for closed loop control, from each time you obtain the current state of the soft robot from the actual sensor. So then you can actually take this input this state into the Q function to get and execute the optimal action for the policy. A soft robot may interact with a wide variety of objects in the environment. where some of the information of these objects and the robot itself cannot be effectively perceived. For example, hardness or weight of an object that the robot tries to pick up can potentially interfere with the interaction. So a few other areas where ML can be applied is within sensor characterization, which involves collecting raw sensor data aligned with the ground truth values in a controlled and monitored environment, such as a lab setting. This data is then typically provided as an input to a neural network to then predict further values such as force, pressure, strain, and location. In contrast, you also have system characterization, which collects sensor data in a less controlled environment that mimics their use within an actual real life scenario or in the field. In this case, ground truth measurements such as force are more difficult to obtain because it's not really in that controlled lab environment anymore. So users often have to circumvent this by mapping to higher level classification, such as grasp success or texture recognition as two examples. Learning controllers function by iteratively evaluating the performance of the resultant trajectory for a controller with respect to some function and updating parameters to increase the performance via optimization. So this is really how learning from a controller can work. And so the Harvard Biodesign Lab is working on cutting edge research in this space to develop a soft robotic glove that provides repetitive stretching, exercise, and grasping assistance to people with limited hand functions due to any sort of neurological conditions. Another area that I think is really exciting is actually within imitation learning for doing complex manipulation tasks from using teleoperation. So I'm actually currently working with Kindred.AI on developing a lot of these techniques for complex manipulation tasks. And imitation learning is essentially taking these robots and helping them learn through the imitation of humans doing the task that they want the robots to do. And so they typically need to be trained on a lot of data and on a series of human demonstrations before they can effectively reproduce the desired behavior. One way to do this is through domain adaptive meta learning. So many demonstrations of many different tasks are performed by both the teleoperated robot and humans, and these are all collected. Then the human demonstration is provided for computing the policy update and evaluating the updated policy using a robot demonstration that is doing and performing the exact same task. So teleoperated medical robot systems are often used. It's a really interesting application where they're used for surgeries, treatments, and diagnostics to be conducted across short or long distances while utilizing some sort of wired or wireless communication network. Robotic manipulation, telecommunications, and vision systems are being developed to further enhance the precision of the robot doing surgery and overall just enhance the research that's in this space. So alongside my other work, for the past few months, I've been working on trying to tackle some of these problems by developing generalization techniques with a company called Hanson Robotics, specifically at the intersection of Neuro-Symbolic AI. So Hanson Robotics is a company behind Sophia the robot, who is a life-size human-like machine who's able to make facial expressions and understand sentences and have conversations with humans. So I'm helping to develop an algorithm within RL and Neuro-Symbolic AI that is able to improve the sensing, perception, and grasping of her arms to allow her to do more tasks and interact with humans. And so the robot will then be used for autism treatment, medical depression treatment, as well as we've presented our research on this at the WIML NeurIPS 2020 and AAS conference this year. The reality is that we don't have artificial general intelligence yet. And the main reason is because we don't have machines that are able to understand or learn any intellectual tasks that a human being can. But robots like Sophia and other humanoids that are being developed today are made up of hardware. And when we compare hardware to humans, they're still not at the same capabilities of humans. If you think about the human brain, we have millions of neurons that are powering in a second, and we're able to compute and process tons of information in a split second. But we're still limited by the hardware as well as the computation that we have on the software side to be able to actually run things and compute things really, really fast. And so this is an area that we really need to focus on. And there's a lot of researchers that are working on key areas within AI to help make this technology more generalizable and robust in general. And the first area is within sensory perception. And so if we think about algorithms like computer vision, which is the ability for these machines to identify objects, process information, we can see that AI systems are still pretty far away from developing human-like sensory perception capabilities. For example, systems that are trained through deep learning still have poor color consistency. And a common example of this is self-driving cars. If you have, let's say, black pieces of tape on a stop sign, that self-driving car will easily not recognize that as a stop sign, but as humans, if we saw that, we would still know that it's a red stop sign and that we have to stop there. And so reality is we don't have, we still need to develop our computer vision algorithms to be able to better understand real life contexts and scenarios, and they're largely limited and incapable of doing this today. The other area that we need to develop is within NLP, or natural language processing. So this is essentially being able to develop systems that can fully understand a language, the complexities between them. And in order to do this, it needs to be able to consume a lot of sources of information with full comprehension, not only to understand what the text is, but also to get the context behind it, to be able to hold conversations and produce text in a way that feels very natural to the way that humans would actually communicate with each other. And the last area that really needs some development is within manipulation. And this is where a lot of research alongside NLP is currently happening. So if you think about humans, it's really easy for us to be able to, let's say, retrieve a set of keys from our pocket, but very few of us would let any robot manipulators or humanoids do this task for us. And the reason is because robots actually find it really difficult to do tasks that require a high amount of precision. And there's a lot of researchers that are working on this problem specifically, like a company such as OpenAI, which showed a demonstration where they trained an RL algorithm to teach a robot hand to actually solve a Rubik's Cube problem, which in itself is a very complex problem. Outside of my work, there's obviously global companies that are also working on these problems, companies like Google Brain, which have a focus on deep learning, companies like OpenAI that are working on making sure that AI is safe and ethical, Facebook Research, which is doing a lot of work specifically within social media, Google DeepMind, which is working on building a lot of Google products that we actually interact with and use on a day-to-day basis. There's also companies like Neuralink that are working on developing a chip that is connected to wires that is able to fan out into the human brain and actually is capable of both recording brain activity and simulating it in a matter of seconds. They've also developed the Neuralink robot, which they use to implant the chip and do surgery because robot precision actually reduces the risk of damage to brain tissue than often humans doing the surgery themselves, as there's a lot of human error involved in that. They recently showcased a monkey with chips embedded on each side of its brain playing Mind Pong. And so although he was trained to move a joystick during the demo, it was actually unplugged. And so he controls the paddle simply by thinking about moving his hand up or down. And they did this by recording and decoding electrical signals from the brain using more than 2,000 electrodes implanted in regions of the monkey's motor cortex that coordinate hand and arm movements. Using this data, they calibrate the decoder by mathematically modeling the relationship between patterns of the neural activity and the different joysticks movements that they produce. So this work has greater implications for potentially curing mental illness, such as anxiety or depression disorders, curing conditions like Alzheimer's, dementia, and spinal cord injuries. And they're also using a lot of techniques within AI to actually help decode some of the sensors and the signals that they're collecting from the brain activity and the EEG signals that they're collecting as well. There's also companies like OpenAI that develop frameworks like GPT-3, which are really pushing forward NLP and being able to understand and process text the way that humans are able to do today. Now, when I think about the future with machine intelligence, I imagine a world where amputees no longer have to buy really expensive, difficult to use prosthetics to live their daily life. I imagine a world where we have affordability and accessibility of prosthetics for nearly 1/10 of the current cost today. I imagine a future where stroke patients are able to easily get access to cheap and effective rehabilitation equipment that will allow them to recover their motor functions. I imagine telerobots being used to enhance intricate procedures during surgery. And what's really, really exciting to me is that we're just touching the tip of what is possible today with machine learning, robotics, and machine intelligence. Thank you so much for your time today. I would love to stay connected with anybody. If anybody has any questions in regards to anything I spoke about, or you just want to reach out and connect, here are some of my social medias. where you can connect with me, or you can also email me directly, and I'm happy to chat anytime.
Amazing, Alishba. Thank you so much for sharing with us. I know this virtual audience has really appreciated your insights and is giving you a huge virtual round of applause. Thank you again. For the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our amazing exhibits. Thanks so much, and we'll see you around.